All right, next up for the second speaker of the day, we have Francesco Lin from Columbia University. He'll tell us about homology cobordism and the geometry of hyperbolic three-manifolds.
Okay, well, thank you very much for the invitation to speak. It's a great pleasure to be here in Miami. Yeah, so I want to tell you a little bit about homology cobordism and the geometry of hyperbolic three-manifolds. Because the general theme that I've been thinking about in the past few years is like, how do Floer homology and hyperbolic geometry interact in three dimension? And in particular, if you have hyperbolic three-manifold, is there anything you can say about the relation between its Floer homology groups and the geometric invariants which are in hyperbolic geometry, such as the volume, the activity radius, length of closed geodesics, and all these things, which by most of the rigidity are topological invariants. So you have this huge collection of topological invariants, between a collection of numbers, for example, and can you use that to say something about Floer homology? Okay, so the work I'll tell you about today is how some topological application of this thing that we're thinking about. So let me just tell you a bit what let me quickly review what the protagonist of this topic. So we'll think about the homology cobordism already to say that P. This is the group of oriented integral homology spheres. And then we consider them up to homology. Okay, so to put this thing to integral homology sphere with an equivalent, there is a W such that the fusion so we look up the coordinates which look like cylinders homology. This is a very important object of study in three-dimensional, because one-dimensional topology, and and it's a huge group. So this is a theorem of the theorem of Buddha, and this that this group contains the infinity, so an infinite random group. And this is actually what shows you that this is generated by the distance field sigma. One. But then positive. The proof of this uses Young-Nielsen. Okay. And I guess much more recently, the theorem. Another theorem about the structure of this group is due to that. And in fact, theta 3 has an infinite sum. And it doesn't just have a subgroup, which is huge, it also has a direct sum, which is huge. I guess, we don't really know much about the structure of this group in general. So for example, is there torsion? Are there visible elements? And these are all open questions. For example, we don't know if this group contains irrational numbers. Once you look in the realm of non-finitely generated Pavilion groups, things like one, you might have. We don't know. Okay. Yes. So this is more or less all we know for this proposal. Well, it's structured as a group. Yes. And so I will be able to say this group uses involved in data. Yeah. Yeah, so I want to, yeah, so we're in 3 dimensions. So, the thing I want to do today is look at this group from the perspective of the generalization. So let's look at theta 3 from this one perspective. Okay, so in particular, Thurston geometrization tells us that you can decompose any three-manifold in pieces which are either ciphered or hyperbolic. So I guess for simplicity, let us consider the general simplest case in which I have ciphered hyperbolic. Can I cipher, for example, cipher manifolds? There's many of them, and they can generate a infinity. But yeah, in some sense, we know that ciphers, from the point of view of Thurston geometrization, cipher manifolds are very rare and few. So in general, if you pick a random three-manifold, it will be hyperbolic. Okay, for example, of the 350 million knots that Sherry talked about, I would say 99.9% are hyperbolic probably. So this is the generic case. So if you want to understand all three-manifolds, hyperbolic ones. Yes. Yeah, so that's what we know how the theta 3 interacts with sorry, I'm losing roles. Yes, how the homology cobordism group interacts with this kind of structure. Well, the cipher case, I guess this theorem of Hendricks, Ohm, Loppergen, and Zemke, 22, confirms that in some sense cipher manifolds are very sparse in the grand scheme of three-manifolds. So in particular, the homology cobordism group is not generated by the cipher manifold. And in fact, they generate a very small group. So in fact, the quotient is not finally generated. And so, from the point of view of pure three-manifold topology, we know that hyperbolic manifold is generally the case, and this tells us, ciphers are rare. And this theorem, upgrade that to also the case of homology. So even if you want to study the homology cobordism group itself, cipher manifolds, are only seen a very small part. Okay, on the other hand, hyperbolic three-manifold. So this again, this is involved. Okay, but yeah, I guess on the other hand, the genericity of hyperbolic three-manifolds also translates to genericity of homology cobordism. This is a much older theorem than Myers. In B3, we show that every class in theta 3 has an hyperbolic extension. And the proof uses geometrization of pattern. Okay, so yeah, so in the grand scheme of things, if you really want to understand the homology groups, homology cobordism in this sense, it would be very interesting to understand how homology cobordism interacts with homology. So I guess maybe that's the main question I want to address today. So, question: how does homology cobordism interact? Hyperbolic geometry. Okay, and again, hyperbolic geometry, this is a topological property. Hyperbolic geometry gives us, tons of polygon invariants, such as volume, the radius, and this is the largest number, such as any point you can find all with that radius in your manifold. Thanks. Physics. So the question that I think is very interesting is whether, given some data about these numbers, the infinite collection of numbers, can you say something about homology cobordism? Yeah, so that's because that allows you to study homology cobordism at large on this problem. Okay. Any question about this? These are logical invariants. Fine. Okay. What Reggie said that if a hyperbolic metric exists, then it's unique polynomial, so that these are things of invariant. That's why hyperbolic invariant. Yes, so this is a super general question that probably this generality is impossible to answer because there isn't a really well-defined question. So let me maybe give you a more precise question, some more precise question. Okay, so yeah, so we have all these numbers. So maybe the simplest number that you look at when you have a hyperbolic manifold, like on the volume and the utility rates, the two real numbers. Yeah, so you can. That's interesting because if you fix a v and an epsilon, then the set of hyperbolic manifold with volume at most v and utility radius of this epsilon is finite. And this follows from the Jorgensen and so there's thematic hyperbolic manifolds, and most of them are good, but there's an actual way to extract a finite using geometrically meaningful finite set bound on these two numbers. Yeah, and in turn, this gives us you can use this to define interesting subgroups of homology coordinates. So you can look at define theta epsilon, and this is the subgroup generated by all integral homology as threes with volume at most v. And I get something that's very common. Injectivity rate is bigger than x. And by definition, well, this is a finite set. So this is a finitely generated subgroup. A nice finitely generated subgroup of theta b. Yeah, and yeah, that's by Meyer's theorem. Implies that the homology coordinate group is the union of all these theta. So this is an exotic objective. And so this is a huge Pavilion group. But yeah, there's a geometrically meaningful projection by finitely generated groups. So hopefully this is a good subgroup. Finitely generated is so much easier to understand. This is a good object to try to understand. Okay, so I guess the basic question is the following. So can we say something? We'll see this law, or should I say something about data? Yes. Can I say, I look at all the manifolds, the body integral on the scale, we're going on almost 1,000. And if you please register is 0.01. Can you say something about the group that there? Well, first of all, it's finitely generated, so we know that it's not anything. So, there is some element outside. So the very basic question is like, can you exhibit an explicit example of a class which does not belong to AWS? And that's the very basic thing on average of word of ranks. Yeah, so this is well, I would say, yeah, so there's two layers of why studying this thing is hard. First of all, this set is finite, the set of manifolds with these properties, but we don't really have a good understanding of what's these generators of this group are. We don't even have a good estimate of how many of these manifolds there are. So we don't have an estimate yet. Ali? Sorry? Yes. Oh, so you pick a knot and do surgery, so the volume will be bounded, but the injective rate is equal to 0. So only finite manual surgery on a given knot will be, yeah. Yeah, thanks. Yeah, so this is, yeah, and of course, then even if you have a description of all these manifolds, it's very hard to study homology or concordance from this manifold. So there's two layers of understanding all the hyperbolic manifold like this and understanding homology cobordism property. Yeah, so I think, yeah, so today I will not, I guess, I mean, I give you values of the epsilon, which have this manifold. It's not there. This is something, a question that interesting. I will not be answering this question today, but I will answering a related question. So yeah, so as I was saying, here these are just the two basic numbers we can look at for hyperbolic manifold. But you have essentially all the invariants that you build out of using the hyperbolic magic turn out to be broad invariants. So you can choose more, the things in my invariant depend. Yeah, so there's an additional invariant I'm thinking about quite a lot. And that's more related to spectral geometry. But yeah, so let me just briefly review what this additional invariant that's we'll think about. The additional body invariant. And this is more, these are very geometric, like being, you have your ruler, you can go manifold and measure this thing. This is more spectral in nature. So you can look at the Laplacian. The Laplacian is equal to star square, and this acts on conforms. Okay, and conforms, and you might call this break as E equals 0. That's so here, let's say, I'll always assume the one here, so U1 0. Yeah, so the forms is composed by the Hodge theorem in exact forms and coexist. Okay, and the Laplacian acts on this, preserving this composition, and it's diagonalized. So you think of it as an infinite dimensional matrix. But yeah, so the spectrum here, Laplacian, would be 0, less than 1 double star, straight on 1 2 star. Okay, so the other quantity, and this is, Laplacian, you can think of it as, somehow related to waves. So this somehow measure the frequency at which certain type of waves vibrate manifold. So the quantity that I'm interested in is from the first time about spectral gap. And this is a so lambda star. And this somehow appears in a lot of unrelated work these days. So but yeah, I'm interested from a point of view. So this is a spectral. Yeah. And it's a very, it's very well studied these days, and there's a lot of problems in different fields that relate to understanding this quantity. But yeah, I guess one thing that we did with my team is that you can give concrete lower bounds for random stars. So yeah, in general, this looks like a very complicated. In fact, these numbers are all easy because once you have a ruler, this is much harder because this equals always some kind of PE. But yeah, it turns out that you can still using this tool, you can configure lower bound from outside in terms of geometry. Okay, as an example. Okay, so there's this nice census of hyperbolic three-manifold with small volume. So in the census number 5, okay, the number 5 manifold in the census, it has volume about 1.39 and interactivity radius about 0.83. And you can show that this has lambda 1 star. These are integral model spheres. This is bigger than 0.04. Okay, so once you have an explicit manifold, we have some tools to give you explicit lower bound on this point. Okay, so even if it's much different in nature, so it's kind of a spectral quantity, you can still understand it in the case of hyperbolic. For example, for census number 34, volume is about 1.91. The activity radius is about 0.24, and you can show lambda star is actually very small, but you can show it's bigger than 0.001. Okay, and just a remark, if you have a integral homology sphere, and this lambda 1 star is bigger than 2, then it's an null space. Okay, so because there's this conjecture was saying that there, essentially there's the only prime integral homology spheres are S3 and the homology spheres. In particular, multi-hyperbolic example, we would expect in general this lambda 1 star to be very small. Well, otherwise we find out. Yeah, but in general, somehow in all the examples with computer with the homology spheres, this number tends to be very, very small. Okay, so this is, but yeah, the point is that you can actually give a complete bond in terms of geometry. It is an null space. Yes. So I guess the conjecture is that no hyperbolic integral homology sphere is a null space. What's sorry? Yeah, here you always assume you're connected there, and I'm looking at the bottom. So this number always tends to be, we have examples of rational homology sphere, which is bigger than 2, bigger than 9. But for integral homology sphere, this number can be very, very small. So this somehow, this somehow convinces me that also that sense. Okay. Yes. So yeah. So now we can, this is the group that we were interested in studying at the beginning. But what I can say about is something which we based on lot on this too. So that was how That's out. Instead of now take the delta epsilon delta, and then you can consider theta the epsilon delta. This is the span. Yes. The rational quantity sphere? We don't know. It's hard, yeah. But it seems, yeah, it's like very out of reach at the moment. So, yeah. Because all we can do is, like, if you give me a complete example, we can complete lambda one star. But there isn't a general way to do it in that. It's a very hard question. No, so yeah, if you're in a period that's very small, the lambda one star that's very small. So manifolds with big lambda one star has somehow lambda geometry. Even if the period is very big, the lambda one star is very small. Somehow they look somehow not big or smaller than the time. Yeah, there's a lower bound when you take the videos. Rational quantities. Not we know. It might be. Yeah, so but yeah, we don't know how to prove that. Yes. So yeah, I guess the definition now. We can guess what the definition would be. So these are this group generated by all integral harmonic spheres with volume less than d, divided bigger than epsilon, and this first eigenvalue at more than this now. Okay, this eigenvalue must be very small, so the natural thing is a lower bound. And again, of course, this again, if you're generated by a subset of this, so this again finally generated. And again, by my experience, this doesn't matter theta bs. Okay. Yes, so this is the thing that I want to tell you about. This is the theorem that I want to tell about this. Okay, given the epsilon delta, there exists a explicitly computable constant and delta such that if you're bigger than this, then the class of the cipher manifold C minus 2, 8n minus 1, 16n minus 1 does not belong to theta. Okay, and here really by explicit, really the interesting part I think is that we can actually it's actually explicit, like it's a elementary function of the epsilon delta. So yeah, let me just give you, for example, if epsilon is 0.15, then you can pick and the 0.15 delta to be the following constant, which is very ugly, very long, but it's explicit. That's 4b times 200 plus exponential of 11 plus 15 times e to the 11 over 2 times b to the 7 over 12 times everybody cosine of 57b minus 1 to the 8/3 times 1 plus 3 divided by delta to the 12, not to the 1/2, I think. That's enough. So this is why we're fighting by explicit. Between the three numbers, I can give you one number that you can write down. And that's, and that gives you an explicit element if you can a number bigger than this, and that won't belong to this group. defining a very hyperbolic geometry. Okay, yeah, and let me just tell you, so this is the main theorem I want to tell you about today. So, this will be some application of relation between the homology and hyperbolic geometry. Yeah, so, this, it's almost all the question that I told you before, the one in which you just look at A of the accident. But essentially it reduces that to a very hard problem to stack the geometry. So remark, by finiteness, there exists a delta, which is delta of the epsilon, such that lambda 1 star is bigger than delta for every y with volume less than b, and just the rate is bigger than x. Okay, just be rational, like okay, just because there's only finite in any of this, and this is always a positive number, you just take a minimum of them, and that will work. Okay, the problem is that there's no explicit constant that we know. Okay, no. Okay, but you can compute it for given yes. In principle. You just do this literal homology sphere with that property, and then you run our technique in philosophy, that is your one for all of them. That's totally impractical. This is practice. This is what people would call an effective bound. Okay, can make it. But there's no explicit content. This is a very complicated. Right. Yeah, in general, given interesting explicit lower bound for lambda 1 star is a very important problem. For example, it's related to this conjecture of Bergeron detachable growth of homological quotient hours by kinetic. This is a kind of question that a lot of people related to. No progress. If some of them is able to actually find a bound, then you can just plug in the lower bound from that here. And then you get a bound, which doesn't involve that. And so you just get an explicit constant that will be in. So, yes. Yeah, these types of spheres are independent. Yeah. So I guess you'll be clear from the post that, yeah. So yeah, somehow. Yeah, now I'll try to give a sketch. But yeah, this spheres are independent. Okay. Yes, any question? All of them. Yeah, so I guess maybe the problem I was saying here is that to compute lambda 1 star here to get the lower bound, we don't just take as input just the volume of the GP trace, but we take as input the whole length, all the lengths of the theoretic at a certain point. We need not just two numbers, but we need like thousands of numbers. Yes. Yeah, so yeah, that's a good question. So, the proof of this result we use P2 monopole homology. So it's it also works for Z2 homology sphere. But the same idea that we'll talk about allows you to prove some for general rational homology sphere, but you don't get the subgroup generated, you just get the specific elements. So I guess P2 is the thing that allows you to go to subgroups rather than a single hyperbolic homology sphere. Yeah, I'll mention that. Oh yeah, by the way, I picked out these two examples because they're the two smallest hyperbolic homology spheres we know about. There's no other smaller example in the sense of it. Because it's not known that they're actually the smallest. Okay, I guess any question before I try to, yeah, I will go give in a yellow proof. Okay, so there are two cases in the proof. Yeah, so there, I guess the part, there's piece A, which is, you know, into monopole homology. And then part B, which is, you know, using an idea of geometric analysis. Transparently. Yeah, but you know, so I got, yeah, so this is the thing that will maybe I'll start with that. So I guess for A, I guess the idea, so if we can bound, so given a bound, you know, so let's look at Floer homology. So you know, I'll look at the use portion. So I look at Floer homology. So I look at the idea standard Floer homology, which is the same as class, if you like, Floer homology better. But yeah, given a bound on the length, you know, these groups, you know, they come with a tower plus some use portion. Right? And this is tower plus the reduced part, which is use portion. So given a bound on length of use portion for all integral homology spheres with volume less than V, conductivity bigger than epsilon, and what's the bigger than no. So suppose you have, you know, suppose that given these three bounds, you can give a bound of the torsion, so how long the two towers are. And then, you know, then first of all, you know, if you look at the connect sound formula, when you take connected sounds or reverse mutation, the U torsion doesn't get bound. Okay, the U torsion stays in. It's just the maximum of the U torsion you see. So get bound on the torsion, then the torsion. Because we have some two things, you know, the length of the U torsion is just the maximum length is just the maximum. Okay. And then given this, once you have a bound on the U torsion, what you can show is that you get a bound on alpha minus gamma. Okay, these are the manual protection terms. Okay. Yes, and these are homological cobordism invariants. So the length of the U torsion is not homological cobordism invariant. You know, you might have a homological cobordism, the U torsion maximum gets arbitrarily big. But yeah, alpha minus gamma is homological cobordism invariant. So from here, this is homological. Okay, and you know, and alpha of yn is manifolds here minus gamma of yn goes to infinity. So, you know, if you get a concrete bound on the length of the U torsions for all the integral homology spheres with this given geometric constraint, you get a bound of alpha minus gamma for all the connected sums. And then, you know, you just get n large enough so that yn has bigger than the bound, and that has, this won't be the group generator. Okay, so this is the input from P2 monopoles. So really what we need to do in order to prove this result is to give this bound amplitude function in terms of the volume, the bit radius, and the geometric. Okay, so that's what the hard case, I would say. Okay, so to do that, D. Okay, so D is bound on U torsion. Here's where ideas from the right analysis perspective come into play. So let me just give you the basic idea. So about the study with monopole homology. So the Saveliev equations, to fix a PC structure. You have two kinds of solutions. There's only one reducible solution. The reducible solution. Zero. So this is the one that's spin or zero. And this is, I throw it a little, that's some smaller solutions, which are the reducible ones. So this is only one, because there are many of them. The reducible solution, it will be D0 plus D, this will 1 4 plus psi. Okay, and I draw this a little thicker because this is, it's a stabilizer. And when you do equivalent things, this thing will give you the power you see the launch. So this gives rise to the power. Okay. But in general, what you see is that there will be a lot of this irreducible solution, but there's only one reducible solution. Okay, and this thing will give the power, and then there will be some flow lines between guys. That's the picture. So there might be some flow lines here. More picture, flow lines. We'll draw something that makes sense. Differential has to square to 0. I guess and then the chain complex. This gives the whole power. You can see that the new torsion, hopefully. That new torsion more or less will all arise from the reducible solution. And so if you can bound the range in which the reducible solutions are, then you can bound on the new torsion. So then new torsion bounded above. Okay, everything here is graded, relatively graded, and so you can bound it above by essentially in terms of the maximum of the grading difference between the reducible solution and any other irreducible solution, any other reducible solution. So this. There will be, I have all these irreducible solutions, and for example, there will be some delta grading here. If you can bound the maximum delta grading, then you will also be bounding the maximum power. Okay. Yes. So now I got the goal. If you want to bound the new power, really want to bound the relative grading between the reducible solution and the reducible one. So now is where the Lin geometry comes in, because this grading has interpretation in terms of spectral flow. So so by the in the same way, the digit in most theory, the difference of grading is the number of positive, how the index changes between the critical points. In infer theory, you can think of that in terms of the APS index theorem, in terms of spectral. So by the APS index theorem, so we can, so the delta gradient between the 0, 0 and any other solution is the psi is interpreted term of spectral flow and right, so you can so you have to count your hashings. Okay, so you start that. Your hashing of the eigenvalues go up and down. Okay, doesn't include many of them. And the spectral flow is exactly the number of eigenvalues that look negative off. Okay, and in the finite dimensional situation, that's exactly the difference of the indices. So this is how you define it in dimensions. And in our situation, the hashing, the family of hashings is L of T. L of T will be the hashing of the Chern-Simons functional and the reducible solution. And then the family is obtained by some kind of multiplication operators. Involving B and sum. And so you have your standard operator, the hashing and the reducible, and then you perturb it using some kind of operator which only depends on the connection. Okay, so yeah, the idea there is to somehow bound how many eigenvalues in this picture go from negative to positive. And that you can do using tools from geometric analysis that I will tell you about. Just 5 minutes. Yes. So you guys give the bound on the epsilon delta using bounds actually on you can this gives you bounds on the side. Okay, really, yeah, these are multiplication operators. So if you really look at what's going on here, for example, delta comes in because that gives you L2 1 bound on B, and then you want L4 bound because this is these are operators. Okay, now these are operators from L2 1 to L2. And multiplication operator, if you want it to be bounded. I guess the idea is the L2 and then the L4. So you need some kind of control on that. So just a remark here. You get L4 bonds. So if you have an epsilon, gives you bound on the constant solid embedding. Okay, so here is one of the key points in geometric analysis that you need. So of course, in general, there is that constant because this theorem is true on any compact manifold. But if you want that explicit bound, then you need extra information, and that extra information comes from solving. Okay, so then this gives you a bound on the perturbation. Okay, because this family is the basic hashing as a given point as a reducible, plus a perturbation that depends on the side. And the bound on the norm, as I'm printed here, is given by the L4 norm side. So then it's about so the idea then this reduces to give bounds to number of eigenvalues of the hashing the reducible, which are bound by some quantity that come from the epsilon. The idea is that, you know, if your eigenvalue is too low, because you have a bound on the perturbation, once you perturb, you kind of move it up to the positive. So once you know, the only eigenvalues that can go connected to positive will be this inside. Okay, and this, in general, this is related to the bylaw. The bylaw tells you how this grows exponentially, asymptotically. But the bylaw is just an asymptotic result, so it doesn't give you explicit bounds. So that, this can be explicitly bounded. For hyperbolic three-manifolds. In terms of DNS. So you can, if you give me DNS, I can tell you a bound on the number of eigenvalues that 1 million of this complete block, explicit block. Yes, and I think I'll stop here.